Welcome to the third PowerPoint for the carbonyls topic, and we're continuing with the reactions of carbonyls. So we're in part 2. The textbook pages still the same, 457 to 459, and as ever, please do pause to reflect when suggested. Make sure you're processing what you're learning, and any problems or questions, just raise those with your tutor. Before we learn some new stuff, let's just recap what we know already. We know, of course, that the aldehyde can be converted to a carboxylic acid via oxidation, and we've just learned a new mechanism for our carbonyl compounds being nucleophilic addition. So the mechanism you can see on this slide here, it's been drawn out for you. Now, if you're asked to describe the mechanism, do make sure you always include the name, remember, and get the spelling of nucleophilic correct. So what is a nucleophile? Well, here for this example, our nucleophile is the hydride ion, and that comes from our reducing agent because this is a reduction reaction because we're adding hydrogen. So we are converting the carbonyl compound back into its original alcohol. Now, for simplicity, we're showing methanol going to methanol, but effectively, this could be anything. So it's important when you draw your intermediate that you pay attention and you reproduce the structure of the molecule correctly. So although you've got to focus on certain aspects of the functional group, do make sure, because one of the marks will come from the correct intermediate. But to get to that intermediate, let's have a look at the first step. So we've got our nucleophile. Nucleophile, remember, is an electron pair donor, so we can see that happening. The pair of electrons is being used to form a new covalent bond between the hydrogen and the carbon. Okay, so simultaneously then the pi bond will break. We've got heterolytic bond fission here, and so both electrons go to the oxygen, so we end up with the oxygen gaining an electron, so you have that negative charge. To convert it then to the alcohol, you need that second hydrogen. That comes from the water, remember. That was why it was important to put AQ for the sodium borohydride. And then, of course, we've got our hydroxide ion that's left over at the end. So when you draw out mechanisms, they're typically worth sort of 4 marks. So it's important that you do begin the story with the permanent dipole across the C double bond O, and then you draw your curly arrows accurately, precisely, telling the story of those bonds being made and broken. Okay, so we're going to carry on now, and we're going to stick with the same mechanism because carbonyls react via nucleophilic addition. Here, the type of reaction there was reduction using a reducing agent. I'm going to show you now a second type of nucleophilic addition reaction with carbonyls that involves something different. We're on page 7 in your notes, and this is the next reaction of carbonyl compounds, this time with hydrogen cyanide. So we can see the displayed formula for hydrogen cyanide, HC triple bond N. Now you'll be pleased to know, even though this is a new reaction, it undergoes the same reaction mechanism, nucleophilic addition. The reactant, hydrogen cyanide, is usually made in situ. Now we've come across this term before, in situ. Think back to the alcohols topic. When we converted the alcohol to the haloalkane, we followed the same kind of thing there. Now, the reagents that we need to use to make the hydrogen cyanide here are sodium cyanide and sulfuric acid. So those two react together in the reaction vessel to make the HCN, which will then react with the carbonyl. Okay, so again, think back to the alcohols booklet just so that you can see the similarities with that reaction that you learnt in year 12. So we're making the HCN first in the vessel, and then the HCN reacts with the carbonyl. Now the reason for making the HCN in situ is linked to safety. you've probably heard of cyanide. So hydrogen cyanide is very poisonous, and you don't want to breathe that in if you can help it. Now, hydrogen cyanide is an extremely poisonous, volatile liquid. Look at the boiling point, 26 degrees centigrade. Think about your temperature of the lab. Room temperature is typically 20 degrees centigrade. Standard temperature is 25 degrees centigrade. So HCN, it's not going to take much to turn that into a gas, and you don't want to inhale that. So you'd certainly be doing this reaction using a fume cupboard. Now, making it in situ will also improve the safety because it will be being made inside the reaction vessel. It will still be extremely hazardous, but part of being a chemist is being able to deal with those hazardous chemicals safely, and you can do that wearing the correct PPE and working in a fume cupboard. It's also going to be increasing the reaction rate. Let's complete the boxes then to summarise this reaction and see what we can learn. So reagents then, sodium cyanide and sulfuric acid. So they react together to form the hydrogen cyanide, which then reacts with the carbonyl. And the carbonyl here has been presented in a generic way. We've got the C double bond O with two R groups either side. And notice we've got R prime and R double prime. So do make sure that you use those little dashes, those primes we call them, to represent them in the equation. So here's our equation. So we're starting with the carbonyl, we're reacting it with the HCN. Have a look at the product, make a note of it, and then we'll see if we can get to grips with what's happening. Okay, you can also represent this using structural formula. So at the moment you've got displayed formula, although there is one bond missing, isn't there, between the O and the H. Now it wasn't required here, but do read that exam question carefully. Okay, if they ask for displayed, display every bond. So that's a bit cheeky. Okay, but there you go. You could also use structural formula. Now, structural formula is quite a skill actually. If you're given a molecule in structural formula, it's important you read it from left to right, remembering that each carbon makes 4 bonds. So if you look at the product, R prime C, then you've got the O and the H, and then another C. So the OH is going to be the alcohol, and then you've got the C and the R. So really a central carbon there. It would be good just to highlight that. That's the one in the centre. And because that carbon makes 4 bonds, you can then see the R, the OH, the R double prime, and the CN coming off it. Okay then, so look, a couple of things to note here. It's an addition reaction for sure because you're adding 2 molecules together to make one product. There's no waste. Now we're going to know the mechanism will be nucleophilic addition. So we know we need a nucleophile, and a nucleophile attacks the partially positive carbon. And if we think back to the reduction reaction, we did convert that carbonyl back to the alcohol. And we've done the same here. So the difference in functional groups, we have got the carbonyls changed and we've now got the alcohol here. So remember I say, play spot the difference. The first thing you're looking for is, has the functional group changed? And it has here. We've gone from carbonyl to alcohol, but hang on, we've got one other thing. This here. This is a new functional group. So we've actually gone from 1 to 2 functional groups, if you will. So we'll have a look at that in a moment. The other thing I've mentioned in the past, but we've not seen it yet, is to look at the number of carbons. Here, we've gone from 1 carbon to 2. Okay, so you're looking for the changes in the functional groups and also the chain length, the carbon chain length, has that changed? So here we've got both things going on. All right, let's have a look at the questions then. Name the 2 functional groups the product contains. Well, one of them we're familiar with, that's the alcohol. The other one is a new one. It's called a nitrile group. Now, because that nitrile group is more important than the alcohol, we have to use a different word for the alcohol, and that's the hydroxyl group or hydroxy group. So the 2 functional groups on their own, hydroxy or hydroxyl and nitrile. And so if you piece those together, the new organic molecule now is a hydroxynitrile. Hydroxynitrile. So it's got the carbon with the OH and the C triple bond N on. It's also sometimes referred to as a cyanohydrin, but hydroxynitrile is what our specification uses. Okay, so this is brand new stuff now. So this type of reaction is very important in synthesis in general. And the question here, why do you think this is? Well, quite an open question, isn't it? But it's really the highlighted bit that's important for us here, because we've actually increased the chain length. Yes, we've changed the functional groups, that's important, but increasing the chain length is something that we might want to do. So this is giving us a way of increasing that chain length. So we've got a new type of compound now, a new homologous series, hydroxynitriles. So we know that we make them from carbonyl compounds, either aldehydes or ketones, reacting with the hydrogen cyanide that's produced in situ from sodium cyanide and sulfuric acid. And there we have our hydroxynitrile product. Now, the next few questions just give you some practice on this equation, and you're also asked to have a go at naming them. So give it a go. It's important to note though that this carbon here is carbon number 1, because the nitrile group, think about it gets the end of the name, so that's the more important of the 2 functional groups. So it's hydroxynitrile, so the hydroxy group here would be in fact on carbon number 2. So you'd have 2 hydroxy and so on. So have a look at the questions that follow, give them a go, and then you can press play again to check your answers. Pentan-2-one and hydrogen cyanide. So here's your equation. So have a look. Does that look similar to what you've done? All right, looking on the right-hand side, your product then is the hydroxynitrile. That's carbon number 1, because that belongs to the nitrile functional group, which is the more important of the 2. Meaning that this is carbon 2. So on carbon 2, you have the hydroxy. Now looking for your longest continuous chain of carbons, we're going to go to the left. And there's 5 carbons in all. Now the OH and the CH3, if they were just hydrogens, then we would call this molecule pentane nitrile. But they're not just hydrogens, they are there. So we've got a methyl group and a hydroxy group. They're both on carbon number 2. So the molecule is called 2-hydroxy, 2-methyl pentane nitrile. So notice here really we haven't, strictly speaking, extended the chain length of the carbons, but we have introduced a branch and we have got our hydroxy and our nitrile functional groups. Question B then, so now we're on to an aldehyde. We can tell it's an aldehyde because the name ends in al, and there's actually 2 of them. So did you notice that when you did the balanced equation? Because both of them will react. So we'd need 2 moles of HCN. So the way it's been drawn here, you can see we've got those 2 CNs. They look like branches down below, but actually that carbon now, remember, is carbon number 1. Or is it that one? Because you've got 2. So you'd have to decide there, and it's all about the symmetry. Because remember, when we name it systematically, we want the lowest lowest numbering in our name. Okay, so it doesn't matter which way we go here. We could start on the left or the right. So I'll start on the left, and if that's carbon number 1, I'll just write that here, carbon 1. Okay, we're looking for the longest chain length, so we'll go up here and then continue across and then down the other side. So we've actually got now 5 carbons. So we've gone from prop to pent. So we've certainly increased the carbon chain length here. So each aldehyde group has allowed us to extend that chain length by 1. So we've now got 5. Now, if those OHs weren't there, that would be a dinitrile. So it would be pentane dinitrile. But they are there, so we need to account for them. It's a hydroxynitrile, and we've got the hydroxy on carbons 2 and 4. And because there are 2 hydroxys, we would say dihydroxy. So putting all that together, 2,4 dihydroxy pentane dinitrile. Now, strictly speaking, you don't really need that dash there. That could just flow as one continuous word. Okay, so hopefully you did okay there. It does come with practice, and hopefully we'll get more practice as we go through, but there you have it, a couple of examples for this new reaction. So you might want to just pause here and just make a flashcard with this new type of molecule on and how you make it, bringing out those key ideas that you are extending the chain length and you're also changing the functional group. Let's have a look at the mechanism then. The mechanism, remember, is nucleophilic addition. We'll use reaction A for our example, pentan-2-one with HCN. So there's our pentan-2-one drawn with the C double bond O displayed so we can see what's going on. We need our nucleophile then. So when we've done the mechanism in the past, our nucleophile was the hydride ion. This time we've got the cyanide ion. So the cyanide ion came from HCN. The bond between H and C has broken and the carbon has gained the electron from the hydrogen, and that's why we've got that negative charge. And it's convention to show that minus charge on the carbon of that cyanide ion. So we've got our nucleophile, we've got our carbonyl, so now let's see how they react with each other. Well, it all begins, remember, with that permanent dipole, so don't forget that's the first thing that you would draw on there. So that's that partially positive carbon that now gets attacked by the nucleophile, and the nucleophile is going to donate a pair of electrons to form a new covalent bond. And when it does so, that pi bond will also break via heterolytic bond fission. So the first step of this mechanism, if you see, it's very similar to the reduction reaction. The only thing we've changed here is the nucleophile, and obviously you change the carbonyl compound to suit the question. The second thing then here, the second part of the drawing is our intermediate. So our intermediate then, we can see the CN is now joined up to the molecule and the oxygen has a negative charge. Now don't worry if you're looking at that and thinking, oh, the CH3 and the CN have swapped places, because it's all about the atoms that they're connected to, remember. The carbon from the nitrile functional group is carbon number 1. So carbon number 2 now will have a methyl group on it and it will have an alcohol, but it's not quite there yet. So we need to pick up a hydrogen. Where will we get that from? or we can get it from the water. That will be a solvent. So again, we show using our curly arrows the making and breaking of the bonds to make that happen. So make sure you've put both permanent dipoles on the water molecules and that the drawing of the curly arrows are precise. When you draw your finished organic product then, here we've got our hydroxynitrile, and don't forget you've got the hydroxide ion as well that's been left over from the water. If they ask you to name it, and only if they ask you, should you then give it a go. Remember, like I've said, carbon number 1 is the C on the nitrile, so you've got the hydroxy in the methyl on carbon 2, so 2-hydroxy, 2-methyl, pentane, nitrile. Just a little bit of repetition here, so you don't have to draw this out, but let's just put it out there again, the mechanism. So you've got your permanent dipole, attack of the nucleophile, breaking of the pi bond, intermediate. Now, at this stage, for this reaction, you could argue that that hydrogen, instead of getting it from water, you could get it from a H+. Because think about it, when the cyanide ion was released, you've got a H+ there. And then it would join up in the same way. So you'd still get the hydroxynitrile, but you just wouldn't need to draw the hydroxide ion as well. Here's an extra question then for you to practice with. If you have got the booklet, you can work on a back page. State and describe the mechanism for the reaction of propanol and hydrogen cyanide. So do pause now and have a go, and then click play to check your answers. The command words here were state and describe, so you need to state the mechanism. That's the name, nucleophilic addition. Make sure you spell that correctly, and that'll definitely be worth some credit. Then the describe, well, that's your diagram showing the curly arrows. So we've got our permanent dipole on the C double bond O. We've got our nucleophile, the cyanide ion, with the curly arrow going from that lone pair on the carbon to the partially positive carbon of the propanol. And then the breaking of the pi bond, shown by the curly arrow. Your intermediate then, to check you've redrawn the rest of the molecule correctly, you've now got the CN attached and the O with the negative charge, and then you're picking up a hydrogen. Now the hydrogen here can come from the water or from a H+, and you've got the curly arrow picking up that proton here to give the hydroxynitrile, and that will be called 2-hydroxybutane nitrile. That brings us to the end of this PowerPoint now, so you can check your progress. You should now be able to describe the nucleophilic addition reactions of carbonyl compounds now with HCN, and that was to form the hydroxynitrile. You should also be able to describe the mechanism following that nucleophilic addition reaction with any aldehyde or ketone that's presented to you, now this time with HCN, where of course it's the cyanide ion this time that is our nucleophile. Okay, so that's the end of this PowerPoint. The next one and the last one for the topic is all about the chemical tests that you can do to identify the presence of a carbonyl compound and also to distinguish between them.